Welcome back, calculus students. In this section of the video notes on limits at infinity and curve sketching, we're going to be taking a look at rational functions and their end behavior. Now, this should be a review of things that you learned in MAT 150 or a previous algebra class. However, we are going to put a calculus spin on each of these examples. So when you originally learned about asymptotes, you learned to compare the ratio of the degree in the numerator and denominator, and you learn to use polynomial long division. We're going to switch this up and we're going to use limits in order to evaluate where the asymptote is. So let's take a look at this first example where the numerator has a degree of 2 and the denominator has a degree of 3. This should have a horizontal asymptote at 0. So let's take a limit as x approaches infinity of f of x, which is the limit as x approaches infinity of this function here. Now the key to this is to use our knowledge of the parent rational function and its asymptotes and turn each of these terms into a rational or constant expression. So you can see that the highest exponent in this problem is an x cubed. That means we're going to factor an x cubed out of every term in the problem. And I'm going to do my algebra outside of the limit. And I'm also going to show you the x cubed term that I factor out, although for the most part I won't. Now, if you take an x cubed out of an x squared, you're actually going to be left with an rational expression, 3 over x. Then we're going to take the x cubed out of the 2x, which is going to leave us with 2x squared. And you can confirm this by distributing it again and imagining how the x's will cancel. In the denominator, if I repeat that process, I'm going to get 4 minus 5 over x squared plus 7 over x cubed. These are going to cancel, and so I'm basically evaluating the limit of everything that's been left behind. Now, using our limit laws, we know that you can separate, so like the limit of 3 over x plus 2 over x squared is the same as the limit of 3 over x plus the limit of 2 over x squared. So that limit can be distributed across the terms. So what we're really looking at for our limit is 0 plus 0 in the numerator and 4 minus 0 plus 0 in the denominator, because as x gets increasingly large, this denominator gets increasingly large, and this whole term will approach 0. Same thing here, here, and here. All of these terms approach 0 as x approaches infinity. So that leaves us with an overall limit of 0. And since the limit as x approaches infinity is 0, we know that we have a horizontal asymptote at y equals 0. Now we could repeat this process for x equals negative infinity, and we would get the same result because 0 can't be positive or negative. Let's try this again with the second example. So our second example, the degree in the numerator and denominator are both linear. They both have an exponent of 1. So we know from our previous algebra classes that the horizontal asymptote is just a ratio of the coefficients 3 over 2. What does that look like in calculus when we're approaching it with a limit? So we have as limit as x approaches infinity of f of x equals the limit as x approaches infinity of 3x minus 1 over 2x plus 5. This time we're going to cancel or factor out an x from every term because that is our highest exponent. And that's going to leave us with 3 minus 1 over x over 2 plus 5 over x. And as x approaches positive, technically, or negative infinity, this term becomes 0, the 1 over x, and the 5 over x also becomes 0. So we're left with a limit that evaluates at 3/2, which means our horizontal asymptote for the second problem is 3/2. Last problem, we have a higher degree in the numerator than we do the denominator. So we know from algebra, if we wanted to find this, we'd have a slant asymptote, and we would need polynomial long division in order to find the equation of that asymptote. For calculus, we're going to take a limit. What is the limit as x approaches infinity for a rational function that has a slant asymptote? Now with this one, I'm going to show you an approach that does not work. So we're going to treat this example exactly like the previous examples, and then we're going to talk about why this doesn't help us solve the problem, back it up, and take a different approach. So in every problem, I have factored out the highest exponent of x. So if I did that to this question, I would get the limit as x approaches infinity of 3 plus 4 over x, since I'm taking out an x squared, over 1 over x plus 2 over x squared. Then in the numerator, the limit evaluates to 3. And in the denominator, the limit evaluates to 0. And we get a divide by 0 error, which doesn't help us evaluate the limit. So I'm going to undo each of these steps. And we're going to take a different approach to the factoring. Instead of taking out an x squared, we're just going to take out an x from each term. And so that's going to give us 3x plus 4 over 1 plus 2 over x. Now the denominator, the limit as x approaches infinity of the denominator is 1. However, if x it gets increasingly large to an infinite value, so does 3x, which means so does 3x plus 4. And so we can see that the limit as x approaches positive infinity is positive infinity. And then if we repeated this process for negative infinity, we would get that it approaches negative infinity. So you can imagine that the slant asymptote looks something like this, causing the function to approach positive infinity. We're going to apply a similar algebraic process for our next example, which is radical functions with their end behavior. Now with this, we have to think a little more creatively. And so we need to kind of think about this radical. The limit as x approaches infinity, and then this is in our denominator, but I just want you to think of really large values of x, really large, infinitely large values of x. In that scheme, we're really not needing this 5, because for very, very large values of x, 4x squared plus 5 is going to be about the same as 4x squared. And if I simplify that, it's basically 2 absolute value of x, since x can be either positive or negative and get the same result. So for very, very, very large values of x, this entire expression is about 2 absolute value of x. This leaves us with the idea that this problem is best solved if we can factor out an absolute value of x. So here's what this process is going to look like. We're going to introduce this factor into our problem, and we're going to introduce it as a reciprocal, so it's really being divided by each term in the problem. So giving myself some space, I am looking at 3x minus 2 over 4x squared plus 5 being equal to 1 over the absolute value of x times 3x minus 2. In any factor I introduce into the numerator, I need to introduce into the denominator to result in a net change of nothing. You know, it's the same expression, mathematically equivalent. We've got 4x squared plus 5. So up here in the numerator, the absolute value of x is just x, and I can go ahead and distribute this term across the top. So I've got 1 over x times 3x, which is 3. And we've got 1 over x times negative 2, which is negative 2 over x. And there's our numerator. In the denominator, I want to be able to put this expression and combine it with the radical. So here's what I'm thinking of. This expression is the result of taking the square root of that value squared. And that would get you 1 over the absolute value of x. By writing it like this, it's now under a square root and can be multiplied to the other square root where you multiply their arguments. So now what we're looking at in our denominator is the square root of 1 over x squared, and we can drop the absolute value because the absolute value of x squared is x squared, times 4x squared plus 5. So as you can see, I have essentially turned this into a rational expression that's equivalent to the original. So I'm going to go ahead and evaluate my limit as x approaches infinity of 3 minus 2 over x over the square root of 4 minus 5 over x squared. So let's think about each term. My numerator, since 2 over x approaches 0 as x approaches infinity, becomes 3 minus 0. And my denominator, since 5 over x squared also approaches 0, is the square root of 4. And so that means that my limit as x approaches infinity is 3 over 2. And that's how I'm going to use this same factoring strategy, this rational problem, to evaluate a radical limit. This is going to be the end of part 2 of the video notes for this lesson. Check back in for part 3 shortly.